PV diagrams. Earlier, we graphed the relationships between pressure, volume, and temperature. We saw a linear relationship between pressure and temperature and between volume and temperature. We also saw an inversely proportional relationship between pressure and volume. While you can graph P versus V, P versus T, or volume versus temperature, most of the time we will be graphing pressure versus volume. These are called PV diagrams. Analyzing PV diagrams is an important part of the AP Physics 2 test. Every point on a PV diagram shows a different state of a gas. Let's look at different processes represented on PV diagrams. To review, an isothermal process is a thermodynamic process where a gas undergoes a change in pressure and volume, but temperature stays constant. Iso means to stay the same, thermal. So isothermal means the temperature stays constant. On a PV diagram, it will look like a gentle 1/x curve, like this. To review, an isovolumetric or isochoric process is a thermodynamic process where a gas undergoes a change in pressure and temperature, but volume stays constant. Isovolumetric, the volume stays constant. On a PV diagram, it will look like a vertical line. You can see the pressure can change. It's going, up or down depending on temperature changes, but the volume stays the same. It is not moving right or left on the graph. Therefore, a vertical line is an isovolumetric process. To review, an isobaric process is a thermodynamic process where a gas undergoes a change in volume and temperature, but pressure stays constant. Isobaric is going to be pressure staying constant. On a PV diagram, it will look like a horizontal line. So, volume is going to increase or decrease depending on temperature, but the pressure stays the same. It does not go up or down. Therefore, you end up with a horizontal line. Let's use what we've learned to analyze different graphs. Note the use of arrows to show you the order in which the processes are taking place. In this case, we can assume the gas starts at A with a certain pressure, temperature, and volume. Then the gas moves from A to B via an isobaric process. So the pressure stays the same. See how it's a horizontal line? So the pressure has not changed. What is happening to the temperature of the gas during this process? Well, think about it this way. If the pressure remains constant, but the volume is increasing, the temperature must also be increasing. You could picture a balloon that's expanding because it's being heated up. As the gas moves from B to C, the pressure is decreasing while the volume remains constant. This is an isovolumetric process. Imagine a rigid container. If the volume is remaining constant, but the pressure is decreasing, what must be happening to the temperature? Well, if the volume stays constant, but there's less and less pressure, that means there's less collisions taking place, which means the molecules aren't moving around as much, which means the temperature must be decreasing. Finally, as the gas moves from C back to its starting position at A, the pressure is increasing while the volume is decreasing. However, this is not a 1/x curve. Therefore, the temperature is also changing. The process from C to A along this line here is not isothermal, isovolumetric, or isobaric. Pressure, volume, and temperature are all changing. It is important to note that since this is a closed cycle, which means the gas returns to the same point that it started at, it will end with the same pressure, volume, and temperature that it started with. If we were instead given the PV diagram shown below, the process of the gas moving from C to A would be isothermal. Here's a PV diagram with actual values. Calculate the temperature at state B if there are 3 moles of an ideal gas. What are the givens? What equation do we have to work with? Here are our givens at point B. So remember, A, B, and C are different states of the gas, so we're only interested in the states of pressure, volume, temperature at point B. So at point B, we have a pressure of 1.5 times 10 to the 5th pascals. We have a volume of 0.05 cubic meters. We were given the fact that there are 3 moles of gas, and the gas constant is 8.31 joules per mole Kelvin, and we're going to use R since we're given lowercase n, the number of moles. Since we're given moles of gas, let's use PV equals nRT instead of PV equals nKT. So we're going to rearrange this equation to solve for temperature because that's what we're looking for in this problem. So we're just going to divide both sides by nR. Then finally we plug in all of our values here, and I have not put in the units just to save space. The temperature is 300 K at point B. Here's another question. At which of these 3 points will the temperature be the highest? Since PV equals nRT, that means that temperature equals pressure times volume over the number of moles times the gas constant. Therefore, we can compare the value of P times V at each point. Since N and R are both constant, since the amount of gas is not changing, we don't really have to worry about those. Therefore, wherever P times V is the greatest, there will be the greatest temperature. The values of pressure and volume are both the greatest at point B. Therefore, that is where the temperature will be the highest.